have some questions that we wanted to discuss, but we'd also like to make this very interactive. So if you have a question while we're talking, please feel free to raise your hand. If the question is something different that's unrelated to what we're discussing, please save that question for the end. But we would like to engage with you as much as possible, as this is also the last session of the day, and we want you guys to be as involved with us as you can. So thank you all for being here this afternoon, and thank you, Donnie, for that intro. We're going to kick off. The goal really today is to talk about collaboration in between the energy industry and the HPC industry and where that collaboration intersects and the importance of it. So to kick things off, really the question that we wanted to start with is why collaboration is important and why is it so difficult to do everything on your own? So Alex, if you'd like to kick off that discussion.
Sure. Well, because we can't do everything by ourselves, right? We all like to think that we're really good at what we're doing, and sure we are, but there are certain things that we cannot do, and I'm saying this specifically from the perspective of an industrial HPC user, right? There are certain things that we know very well about our business, or so we hope, about how we need HPC to work, what we need it for, but especially on the technology side, on the how to do HPC specifically, that is something that we do not have the expertise always. So that is, you know, maybe it's an obvious answer, but it's still, I think, is worthwhile repeating. And you know, especially looking at the national labs or places like that, we do need these as partners to write software. I mean, we heard Mike Rue earlier, you know, representing the software technologies part of the ECP. That's, I think, a good example of where we need collaboration.
Good. Yeah, and I mean, to kind of piggyback on that, there's a huge amount of development work in the DOE space and at the national labs, especially like Mike Crew mentioned the E4S. It's a, you know, collectively billion-dollar effort probably to build all this, and people should take advantage of it. If you want to still do things in the same way on the same hardware, you probably don't need to reach out. But as hardware evolves, as software styles evolve, you know, taking advantage of open source and learning from the DOE labs, even if you don't pick up the code and use it wholesale, getting ideas from people who have been to the mountain ahead of you is really useful.
You want me to go? Okay. I'm David's digital twin over at Oak Ridge, so I manage the industry partnership program there, and sometimes in collaboration with David, sometimes in competition with David. Why collaborate? Well, from a lab perspective, it's important for us because it helps us to get access to real-world problems. We basically engage in more fundamental research. And when we get a chance to collaborate with industry, we get to see how that fundamental research is applied to real-world problems. That's very exciting for us, and it really motivates us. And it also helps to set the direction for future research. We see what's missing and what we need to do, and it gives us a lot of perspective. So we benefit quite a bit from the collaboration. We hope that the companies that come to us benefit too, because we can bring expertise that they may not have. So I think it can work for both sides. I don't see it really as a one-way situation.
Yeah, I agree with all the panelists. I was thinking about this question. It seems like a really easy question. Why collaborate? We're all in this room. This is what we're doing. So what does collaboration mean sort of beyond the obvious? I mean, Alex is saying, you know, it's obvious we need partners to do things, but sometimes for me, coming to conferences like this or just talking with people is really a time to think. I can see people with their laptops open doing their emails, but hopefully you've had a little bit of time during these conferences to just stop and not look at your emails and not do that sort of thing and get ideas from other people, probably ideas which are contrary to your own ideas as well. And I think that's a very important part of collaboration as well, beyond the sort of, you know, learning from the mistakes from other people as well. So.
Great. Thank you. Thank you all for that insight. David Martin, you brought up the DOE just now when you were answering, and so how do you think that working with the DOE, and Susie, this question is for you as well, has influenced the industry's thinking when it comes to high-performance computing, to AI, et cetera?
Well, first, DOE tends to have the largest supercomputers at any point in time. And that's not a criticism of industry, but no board of directors is going to spend $1 billion for a supercomputer that's out of date in 6 years. DOE doesn't like doing it either, but they do it, right? And so, first off, you know, working with the labs gives you a crystal ball look into what your computing future can be. I mean, it gives you access to technology, tools, techniques, and expertise that you probably haven't had exposure to yet. And in a very, hopefully, smooth way, you can have that. And you can start to predict what you could do when this technology comes down to the broader market. DOE tries to do this because the country, fortunately, believes in investing in advanced R&D, and they know that you need these large systems to do that. And so, you know, you can plan, and DOE helps to de-risk the process by taking the first of these technologies and pushing and proving them out. And you can learn a lot from the mistakes and the stumbles that we have.
Yeah, and I mean, we buy, you know, serial number one of all kinds of machines. And you hear about the big ones that, you know, we deploy and build into the leadership class systems, but you probably don't hear about all the other things that we try, and there are dead ends, and there are things that vendors decide not to go forward with. And so we spend a lot of time investigating, and we try to share all that information as much as we can. I mean, we're under NDAs in some cases, but a lot of times the techniques or the type of computing that we're doing is widely available, and we give talks at, you know, meetings like this. That was why Mike Haru came here. And so I like the word de-risk, because it doesn't make it free to learn these things. You still have to do a lot of work, but it lowers the risk a lot to help understand where the technology is going and where the pitfalls are.
Great, yeah, thank you. Thank you for those answers. And that's a great perspective, but I would like to ask David and Alex from the industry side what they have learned from maybe some of the mistakes made by different national labs, you know, to shake up some controversy on this.
So first of all, thank you very much for spending my tax money unwisely by buying a huge machine which will be out of date shortly. I think for HPC, we all know HPC. The hardest problem in HPC is scaling. So it's very easy to build a little machine. It's very hard to build a big machine and run it at scale. So what you're doing in the national labs, of course, is building something 10 times as big as we will build, or really you're building it 5 years before we would build it. So it's really a look into the future of how you do the scale up and how you scale out. It's going to seem a bit weird. Most people know me that I'm the hardware guy, but the hardware is not actually the hard bit normally. The software is the hard bit. So yes, networks and power and all those sorts of things, you have to get it right, you have to work it out, but really the hard work is done at the software layer. I forget the numbers, but I think the ECP spent half of the money on software, something like $1 billion, just writing software for the machines. And it had to start many, many years ahead before the machine existed. So probably one of the learnings for me is really about thinking about scale, but thinking about software at scale. That's probably the hardest learning to have.
There's a question right here. Sorry to interrupt you.
HPC and energy, I mean, governments, not just here, but in other places too, have some pretty aggressive goals for decarbonization with deadlines. And, you know, I guess I would expect the contribution to that progress to come both from changes in practice as the energy companies are doing, but also technology advances. I mean, the GPUs were kind of a godsend for getting exascale systems were energy efficient. Is there anything else that kind of in the wood, behind the woodwork or anything like that? Where is the next big technology advance going to come from that's going to help get toward those goals?
Well, so one of the really interesting things is these systems use a lot of power, but they also ramp up and down pretty quickly. And so we're spending a lot of time looking at tuning applications to use less power. So, you know, if you have an application that's, 10% of peak, for example, if you can get it up to 50% of peak, you know, you're basically reducing the power requirements massively. So a lot of this is not necessarily around the physical work around making machines, you know, use less power or recapture heat or something, so much as just, I mean, the dirty secret for most HPC is a lot of applications, you know, run at 10% of peak or are limited in storage or bandwidth or things. And so I think especially as we're deploying these exaflop systems, getting really efficient code running is a huge win for power efficiency.
I think you meant to say zetaflop systems in relation to these targets.
Zetaflop will be next week.
So I had a related question. So I recently became aware of this this code called GEOS that's being done as a collaboration between Livermore and Chevron and Total, and this is, people are using it for simulation of carbon capture and storage. And so for some of these cutting edge new applications, I'm wondering whether there are actually many such collaborations across companies or whether things are still siloed. Because it's one thing to be like using the MPI implementation that was done by Argonne or using SPAC and saying we're using all the software. How much are people really working together?
Think about how to quantify that, but an easy answer is, especially for this audience, more than one might think. And so similar to how oil companies work together, and I think that's a bit better known on the upstream exploration projects, right? None of those big exploration projects is done by any single company. It's always a joint venture out of 1, 2, 3, multiple. And similarly, a lot of software development projects or even research projects like this project around GEOS are done in collaboration. So for example, the reservoir simulation tool that we're using in production today is a joint development by Schlumberger, Chevron, and Total. So in that sense, that example around GEOS fits right into that, because I think, well, back to collaboration, and not just we, Chevron, we in this industry recognize that those are things that are too big for us to do, where each player brings their own expertise or code into that partnership, and I think that is very valuable. I mean, that's also difficult. Let's not kid ourselves, right? Doing anything in a big company is hard. Doing that between multiple companies and then also throwing a national lab in there and a university, by the way, Stanford is part of that as well, it doesn't make it any easier. But I personally think, and obviously everybody involved in that collaboration thinks that too, there is something to gain from, if we take on that extra thing. And with more software or HPC projects getting more towards integration of different disciplines, because that is kind of a big trend. As we go down that road further and further, we will need more collaboration because there is no single player that knows everything about all the different things involved. So bringing parties together on the domain science side, but also on the technical side, I think we'll see that more. And I think it's a good thing.
So I can kind of give you a couple of examples. One is like the WarpX code that was developed as part of ECP. So for example, TAA Technologies, which is a fusion startup, has started using that as the base for all of their code. And that's being picked up by several different organizations. And so they're getting two benefits. One, they get code that's already built. They're also tapping into a community that they can rely on, where they used to only have a few people who were experts in their own proprietary code. Now they have a community. And so they've found, recruiting and training people is a lot easier. The other thing that's really been taking off a lot in industry is SPAC, which was developed as a DOE project, but is now widely used as a deployment and build environment, which you know about, I'm sure. So things like that, a lot of base layer stuff. We're still not seeing people maybe picking up cosmology code from DOE and running it widely. but the base layer stuff is really taking off in a lot of environments.
How do you prioritize which projects to take on?
That's a great question, and I'm glad that. Oh, were you asking it for internally or for me? Okay. That's a superb question, and it's a very systematic process. There are 3 different pathways to apply for time to one of the DOE user facilities where the supercomputers are, at least for Argonne and Oak Ridge. There are 3 programs. You can apply for time, you fill out the applications. 2 of them are annual calls for proposals. One of them, which is managed at the local level at this facility, is open all year long. All the proposals are peer-reviewed and selected through a peer-reviewed proposal process. So it's very equitable. And they're all peer-reviewed, by experts in the area. As far as industry is concerned, we're agnostic as to the size of your company, small, medium, large. In fact, I can tell you that some of the most exciting problems that we've had have been from the small companies. We've learned through experience that just because you're a big company doesn't necessarily mean you're doing big computing. That there are some very aggressive and very capable small companies with very smart people. They've left large organizations or universities and started something. They just don't have access to big computers to do the problem solving. So, I mean, any of us, I won't go through all the different programs on the ways to apply, but we can talk with you at any time. And I would encourage you, if you're interested in getting access to these supercomputers, to investigate the programs. They all have slightly different requirements, the scale, depending on the scale of what you're applying for. But I think the peer-reviewed proposal process ensures that we're getting, that everybody gets a fair shake when their stuff is reviewed, but also that we're getting the most interesting cutting-edge science problems and engineering problems that are appropriate for these systems that, as we've already discussed, are very expensive and they're taxpayer funded, and we want to make sure we're being good stewards of that. Does that help? Anyone else? Oh.
Any other questions from the audience? No? Okay. So something that you said earlier just brought about the need for collaboration because we don't know everything and there's no way that you could. So given that we're seeing problems become more complex, problems becoming larger, and the need for collaboration growing, what skills do you think that we will need both as scientists, as researchers, as engineers, as people that work in the tech side of things that maybe aren't subject matter experts? What skills do you all think will be required as we move forward into this more complex future in energy?
Sure, I can go first. So I'll answer the question kind of in a sideways way. Yes, there are a number of specific skills that we need, and I'm sure others will add to that. But one key thing is that I think we need is the skill to work, sorry, there's collaboration in this too, skills that help to work across disciplines, which, because like I said earlier, even today, the codes that we write, the codes that we use, the problems that we're trying to solve are rarely single disciplinary, right? Even seismic imaging, the granddaddy of HPC or grandma, I don't know, in oil and gas, even that combines, geophysical knowledge and skills with HPC. And I see that growing. So to me, that will be the key skill or capability or behavior to collaborate across that. I think I'll leave it at that.
Sure. Kind of another skill that I think we see really emerging is the capability of merging data and simulation together. Especially the Department of Energy has something called the Integrated Research Infrastructure, which is an attempt to take physical experimental facilities and kind of merge them in with data and computing. And so the idea is that you'll be able to do things around AI or data analytics or simulation and be able to feed that information quickly back to something. It's an idea that's common in manufacturing through the digital twin idea as well. And so what we're seeing more and more is people who are computing need to be able to interface to the physical world and understand data analytics and retrieving data and compressing and throwing away, you know, data as it comes in. And then we need the people at the physical facilities to start really integrating computing into what they're building and do it, you know, instead of doing analysis after the fact, do computing in real time or near real time on the systems. So I think that's a real emerging area. And the AI kind of plays into that, but it's not just AI, it's just the idea of using data intelligently to make decisions quickly.
Yeah, so obviously all the technical skills you need in the market are critical for what you do, but I think some of the hardest skills, and it's going to sound, you know, the whole lifelong learning thing and all that sort of stuff, but it is extremely hard, particularly when you are as technical as a lot of people in this room are, is because the market changes so much and because the technology changes so much, to have that ability to really throw away your learning, the way you used to do things, the things you did 10 years ago. I was a sysadmin, you know, 20 years ago. Do not put me on a keyboard now, it would be a disaster. So being able to sort of almost throw away your learning to learn the new things and just say, well, I can't do that anymore, I have to do it differently now. And do that 10 times in your career is extremely difficult. And to be able to think like that and be able to keep moving and, you know, innovation, how do you take other ideas and how do you incorporate them? Finding that in people is extremely hard. Teaching people that is impossible. You kind of have to want to do it. You have to be comfortable with it. So I think that's one of the hardest skills to find in the industry. I'm sure it's not unique to this industry. Lots of industries change at rapid pace, and being part of that change is very hard.
I guess I have two thoughts. One is be patient. Labs and companies are different animals, and we're trying to get them to come together. And that can be sometimes a challenging administrative process. So when you think about collaborating with a lab, just stay calm. We'll get through it. There can be some paperwork with it, so don't get upset. All of the administrative stuff aside, I would say shoot for the moon when you think about collaborating with a lab. Our experience has been in talking with companies that almost every company has problems sitting on the shelf that they would like to solve. And they're not solving them and addressing them now in a lot of cases because they don't have the computing that they need. And this isn't a criticism. Everybody has to work within their budget. You're told that this is what you have, this is what we have in our data center, this is what we can accommodate. But when you come to a lab, you can get a lot more than that. And so you can bring those problems that have been sitting on the shelf for whatever reason, where you're waiting until we upgrade our center or we get access to this technology or we get access to that. Start to poke around at the labs. You may find that what you need is there. And those dreams that you've parked for a while, you may be able to bring them out and collaborate with the lab and push forward on them.
Thank you, Susie. And well, thank you all, but I would like to follow up on what you just said, because you brought up some good points about some successes that you have seen in your career when it comes to this type of collaboration. This question is for everyone, but what are, apart from the successes, some of the failures that you've seen or some of the shortcomings? And, you know, how do you overcome those? What are the more positive outcomes that you have found when it comes to industry and the national labs collaborating? And what can we do better as we move forward?
Well, I'm not on the science side of this equation. I'm on the partnership side. So I would not probably be the right one to say what has happened, you know, from a science perspective on particular problems. But let me talk about some of the other things that have to happen when you collaborate.
Absolutely.
One is the labs have to get better in encouraging these collaborations and setting them up. The intellectual property rules and regulations can be daunting. and working through those with companies, especially with large companies who have very large legal staffs and they have very definite things that they want to achieve and protections that they want. That can be challenging, and there needs to be give and take on both sides. And sometimes the labs need to give, it's just my opinion, sometimes the labs need to be a little bit more flexible. Now, there's some things also where companies have to realize by statute, we can't change something. I mean, it's the law that we have to do things in a certain way. And that can be frustrating sometimes for companies, because sometimes we don't have the leeway we need or that a company would want because of the law. And it just takes talking with each other. So when you think about working with a lab, set aside time, because some people get frustrated and they'll walk away. And I would hate to see that happen when there's good science and good engineering collaborations out there that we could pursue.
Absolutely, and that's a wonderful perspective. I appreciate you sharing. David, would you like to?
Yeah, I think the answer is exactly the same, but the other way around from our point of view is that sometimes it is very frustrating and it takes time and it takes money. And time is money, of course, if we only have so many resources internally. And then that puts pressure internally. Why are you bothering to do this thing? It's not bringing any money to the bottom line. It's a waste of time. So sometimes it's difficult to be able to argue internally why you bother to do this. And then that can also sort of drive, accidental failure, which means then you don't try again. You just say, well, it never worked. So, we couldn't do this. So it's the same, but the other way around. It's very, the failures tend to be when you don't see the sort of results people expect. Now, hopefully you go into these sorts of things with the idea that it's okay that it doesn't work sometimes, or, if you're trying something hard, sometimes it is hard and it's not going to work. But of course, at some point I have to go back to my boss and explain why my people didn't do the other work and did this work. So, it's still hard.
Okay. All right. Well, so, you ask about failures, and I think the times that we see things fail is when the expectations up front aren't really set at the right level. I mean, the labs are very good at working on kind of blue sky things and really game changers. We're not as good at working on something that's an immediate need. There's a product or there's a service that is, having problems and it needs a quick fix. Because it takes a while to build the collaboration, even beyond, Susie mentioned the paperwork and the intellectual property rules, even beyond that, just building the level of trust between the teams so that you really trust each other to try things out and to share real, issues that come up, I think takes a while. And so the best projects that we've had are ones where it's kind of something that really changes the paradigm in a way, and really changes how people are approaching a problem, either from a physical standpoint or computational or in new ways. And so those are the ones, and it's hard for companies to make that commitment. Making a leap is a lot different than just, can you get me 10% more efficient engines or something? I mean, where we excel is more like, can you run these engines on totally different fuels to make them more efficient, rather than just, tweak systems a little bit.
So you said that one of the biggest issues is when you have unrealistic expectations in the beginning. Have you been in a situation where you had to deal with that head on? How do you change that dynamic and that discussion at the beginning so that you can have a successful project moving forward and collaborating?
Yeah. Do you want to?
Sure. Well, I mean, in a way, you gave a big part of, or at least of my answer there yourself. It's make that clear, define whether you want to broaden your scope. Do you want to try out lots of things, or do you want to maybe quickly narrow it down to one solution that works and you don't care what the other 15 alternatives are? Do you want to develop new things, or do you just want to make that better? So yes, we had some situations like that. Again, the specific recommendation is really make that clear what the expectations are. How do you measure that? How many new things do you want to try out, and which things do you want to exclude, knowing that that might not be a good idea to exclude, but for time, budget reason, or whatever, you want to focus on specific items of that. And yeah, that's I guess it's going back a little bit back to the previous question, because my mind was still there. The time, but also the scope, right? making sure that both sides know what they get out of that and what's expected and who does what. That's another thing. That's I think is a common theme. We thought you guys were going to work on that. It's like, well, it's your code. You need to do that kind of situation.
So I have just a comment on, being clear, but with these large agreements, you also have to be careful not to be so precise, because even while you're making the agreement, you're going to identify other opportunities or things you wanted to change. And to Susie's comment about the front-end legal lift, you really don't want to go back after you've established agreement and then try to add something major or change something that's going to change the framework, because you almost have to start over. So think about sort of your scope of work very clearly up front. Don't be so precise that if you decide you don't want to do that thing, make it where you can do other things in the context of the collaboration, because it can be really painful and frustrating. And also size your project for the agreement. If you're working together for a year, don't do what I actually did and pick a 4 or 5 year project, which again, it's not a failure, but go and look. We did that. We did a nice project with Argonne, and we accomplished a lot of things. And so look through, if you didn't meet all your objectives, kind of look through what you did get out of it, because it established a lot of good connections with Susie and David. And really, I think we got more out of the project since we finished a project that we ran last year than we did in the project. And that was kind of a multifaceted benefit. So look for what you can get out of it, even if you don't meet all your objectives, especially if it's a research project.
It's a good point, and not to get too specific there, but there are different forms of collaboration or contracts, right, that can meet different sizes. So yeah, good point.
I think we have time. Oh, go ahead.
Well, just to follow up on that, one of the things that the labs are really good at is just blue skying. And even before there's any legal agreement, I encourage you to, just have conversations, because that's usually the way the collaborations start. I mean, certainly when you start doing heavy-duty work, you need some sort of agreement, but the conversations are a lot of times get people over the hump without any particular funding or agreement.
I think we have time for a question or two from the audience, if anyone has. Oh.
So I wanted to just follow up on the issue of the legal agreements. So having been inside the ECP project, I can tell you that the process needs to be streamlined. I had 15 NDAs, and there were meetings that I was excluded from because Oak Ridge was not a party to all of the other multi-institutional things, and Buddy Bland had tried to spearhead this multi-institutional agreement that he ultimately just crashed and burned on, and he said, forget it. I'm not gonna do it, right? And so I think that when we don't have a project that has like the lifespan of the ECP, that somehow you have to become a little bit more nimble. Otherwise, we're never going to get the agreements in place to even be able to move forward. And then one last thing about that, which is when you're buying these really big systems, I've seen multiple times where you could benefit from some outside input before the NRE contracts are signed. And so I understand that there are reasons why you can't bring in outsiders when you're still evaluating the contracts and whatnot. But it ends up being problematic when something key gets left out, and then there's no way to fix it because all the NRE money is committed before. And I can tell you, I've seen this, time and time again on these big DOE systems where somebody left out some wires that nobody was paying attention to, so certain capabilities couldn't be used on an Argonne supercomputer or other things.
Well, let me respond a little bit to a couple of these things regarding doing agreements that cross the labs. The labs are not a monolith. We are all part of DOE, but every single lab, there are 17 of them, they all have their own way of doing something. You're all here from the energy industry. Every one of your companies does something a little bit differently. If you tried to bring 6 or 7 or 10 of you together into some kind of a collaboration, your lawyers would be going crazy, okay? Just like ours do too when you bring all the labs together. I'm not saying I'm not using that as an excuse. I'm just saying it's challenging. You have to think of each lab almost as its own independent legal entity, which by the way it is, you know, because the labs are all managed by outside contractors. We're not part of DOE oversees it all, but we're government-owned, contractor operated. So we're all under different management systems. So it is a challenge. It's a challenge for us too. And all we can do is try to continue to work better. And you know, the labs, the legal staffs know each other, and they do try and work collaboratively on that. We just need to be constantly vigilant. But remember that the labs are separate. I think people sometimes think, well, you're DOE, you know, you're all the same. And we really aren't. We collaborate, but we compete like heck too. So that's maybe one thing to keep in mind. I'm going to punt on the NRE to my colleague down here on the right and how some of that works, because you're probably a little more knowledgeable about that than I am.
I mean, it is an issue that we do it ourselves. We bring in a lot of outside reviews when we go through the different critical decision points in DOE, but we tend not to do that early on. And you have good timing because we actually have a ALCF4 kickoff meeting on Friday, so I will pass that along, that we should have people involved a little earlier.
Wonderful. Well, thank you all for your insights. It seems like we are going to continue moving forward collaborating, which is great. Before we wrap up, I'd like to bring up Livia. Oh, we can wrap up? Okay.
Before you end, may I make one last comment to the...
Okay, but please don't go.
No, okay. I just want to make one last comment. Look, I don't know how many people in here are really familiar with the user facilities in the DOE system, or Argonne and Oak Ridge individually. These supercomputers are available to you. And David made a very cogent remark. He said, well, thank you for telling us how much of our tax dollars you're spending. Let me just be really straight. If anybody in here has a problem that would benefit from access to these supercomputers and you are not pursuing that, you are leaving money on the table. I mean, it is just that plain and simple. You have paid for these systems. Now, you have to go through the peer review proposal process, but go back, ask your teams, do we have problems sitting on the shelf? What are we not doing that we could do if maybe we could do a proof of concept first at a DOE lab? Take advantage of these resources, investigate them if you haven't. We're happy to all have conversations with you. I just don't want you to miss out.
Okay, thank you very much for the comment. Okay, before you go, let's thank our panel again. All right, thank you.